Let's calculate the pH of a solution that has a concentration of 1.0 times 10 to the minus 8 molarities of the sodium hydroxide. First question we ask ourselves is it a single solute or is it a reaction? It's a single solute. Is it a acid, a base, or a salt? It's a base. Is it strong or weak? Strong. And what does that tell us? Since it's a strong base, well, that tells us it's going to break up 100%. So then we write the dissociation of our sodium hydroxide, which breaks up into our sodium ions and hydroxide ions. And since it's a strong base, we know it's going to break up 100%, which means I get 1.0 times 10 to the minus 8 molarity of sodium, 1.0 times 10 to the minus 8 molarity of hydroxide. We're looking for the pH, so the sodium is not something I'm going to worry about in this case. So the only thing we got to worry about is the hydroxide. So I can calculate the pOH by doing the negative log of the hydroxide concentration, which is negative log of 1.0 times 10 to the minus 8, which gets us a pOH of 8.00. Now that I want pH, I will just have to subtract that value from 14. So I get 14 minus pOH is 14 minus 8.00, which gives me 6.00. At this point in time, I usually want you to ask yourself a question. That is, does the answer make sense? Well, we're dealing with a base, and we got a pH of 6, which is an acidic pH. So does the answer make sense? The answer is no. So if you look at the problem, did we do anything wrong? Well, it's a strong base, breaks up 100%, nothing there. pOH calculation looks fine. pH calculation is fine. So where did we go wrong? Where is their mistake? Okay, obviously the answer does not make sense because this is a base, so I shouldn't have a pH that's a acidic pH. Well, the problem goes in wrong is when you go back and you look at the concentration of the sodium hydroxide, it's 10 to the minus 8. If you recall, when we neglect water as our reaction, we usually said check the hydronium or hydroxide concentration and see if it's greater than 10 to the minus 6. If it is, then we can neglect water. Well, notice the concentration of the sodium hydroxide by itself is only 10 to the minus 8. That's less than the concentration of hydronium hydroxide you expect from pure water. So sodium hydroxide is not the principal reaction. In this case, water is the principal reaction, so I got to worry about water. The principal reaction is the water, not the sodium hydroxide. Therefore, we can't neglect the water. We must rework the problem with the water equilibrium and include that additional base from that sodium hydroxide. So in essence, we would write sodium hydroxide goes to sodium ions plus hydroxide ions. We know the concentration is 1.0 times 10 to the minus 8 molarity for the hydroxide, but the principal reaction is the water. So you have water plus water forming hydronium ions plus hydroxide ions. And we know to figure out that equilibrium through Kw, we have a relationship of hydronium of X and hydroxide at X. Which we plug into that equation and solve for. But since I have some hydroxide coming from that sodium hydroxide, I have to account for that as well, which means I have for the hydroxide X plus 1.0 times 10 to the negative 8. Those are the values that we would plug into our equation and solve for X. When we do that, we end up with a pH of about 7.02. Now, I'm not concerned about this calculation directly, so I just wanted to bring to your attention, because I say many times about the water, that we neglected in this course. We're going to neglect it all times except for one problem, which is this one right here. I just want you to realize when you ask yourself questions and looking for if it makes sense or not, that can tell you if you did something wrong, if you're neglecting something wrong, or etc. In this case, we were making a poor assumption of saying that water is not the principal reaction. We would have figured that out by asking ourselves the question, does the answer make sense? You have to look at it and say, something else is going on, we need to fix that. Now, you will have to do some calculations like this where you have some solute breaking up and then you got to use that as part of the equilibrium, but that will be when we get to buffers, etc. And I'll talk more about that when we get there. But I just wanted you to realize that, we're neglecting water all the time, but that's not the case always. It's only in this course right now that we're doing that. Another topic that we're going to cover in just a little detail, not a lot of detail, is the pH of polyprotic acids. Some acids have 2 or more protons, meaning hydrogen ions, to donate in aqueous solution. These are referred to as polyprotic acids. These could get to some very complex calculations when you got a couple of ionizations you have to deal with. So we're going to just handle the simple case of we're talking about a pure acid, okay, or we may talk about the conjugate base concentration. So there's only a couple of calculations. What's in the homework is what we're going to concentrate on. When you get to quantitative analysis, they will talk more about polyprotic acids and their ionizations and handle those calculations. So let's take sulfuric acid, for example. It basically has, first ionization, you have H2SO4, your sulfuric acid. It's going to donate 1 proton, and when we do polyprotic acids, we do 1 proton at a time. So it will donate 1 proton, okay, which forms hydronium ion and HSO4 minus. Well, now that HSO4 minus can also undergo ionization, which is be a second ionization. So I have HSO4 minus now. That will now donate a proton and form hydronium ion and SO4 2 minus. And you also still have in the background the water-water equilibrium. So in essence, if I wanted the total hydronium ion concentration of sulfuric acid in water, then I would have to account for all 3 hydronium ion concentrations. I would have to account for the H3O plus coming from the sulfuric acid, as well as the H3O plus coming from the bisulfate, as well as the H3O plus coming from the water equilibrium. But usually we can make some assumptions and simplify calculations. Let's think about this. We have a strong acid, H2SO4. It's going to break up 100% and form my HSO4 minus. Okay, so it's breaking up 100% and forming my HSO4 minus. Then that's going to ionize. Well, since it has that negative charge on it, it's not going to be able to ionize as great because that negative charge is going to pull on that hydrogen more, so it's not going to produce as many H pluses. So then the amount of H3O plus that's going to form is going to be even less than the amount that we got from the first equilibrium. So what happens then is that we can neglect the hydronium ion concentration coming from that H3O plus, from that HSO4 minus. And as we talked about before, we can neglect that hydronium ion concentration coming from the water-water. So in essence, we're only looking at that principal reaction of the H2SO4. Now, typically we only worry about the principal reaction. So if I was given a pure acid, say H2SO4, which equilibrium will I concentrate on? That would be just the first one because it's in it. So I would only be concerned about the first equilibrium. Now what happens if I was given some salt, maybe sodium bisulfate? Okay. Well, that bisulfate, a part of that salt, I'm going to want the equilibrium that's only associated with that bisulfate, which would mean the second equilibrium. So if I was given H2SO4, I would only worry about the first equilibrium, okay, only the first one. If I was given sodium bisulfate, I would be worried about the second equilibrium and neglect the other two. What about starting off with a weak acid instead of a strong one? We notice in the strong one that it ionizes to 100%, so therefore when it comes to the second ionization, it's ionizing far less, so therefore we know we can get rid of the hydronium ion. Does that still happen when I do start off with a weak one? Well, once again, you have your first equilibrium, which is your carbonic acid, forming your hydronium ion and your bicarbonate ion. Then your bicarbonate ion will now undergo ionization and form hydronium ion and carbonate ion, and you still have your water-water equilibrium. Once again, the total hydronium ion concentration will be the sum of all three. your carbonic acid, your bicarbonate ion, and your water. Once again, let's look at what's going on. I got H2CO3. It's ionizing. It's a weak acid. Therefore, it's ionizing less than 5% to form my HCO3 minus. Well, when I do my HCO3 minus, once again, I have a charged species again. So when I do my ionization for my bicarbonate ion, that charged species is going to pull on a hydrogen more. Therefore, I have less hydrogen being ionized. So I'm going to have even less than 5% ionizing to form hydronium, which means the amount of hydronium coming from the bicarbonate compared to the carbonic acid is far less, which means I can neglect it. And once again, the water is contributing very little. Therefore, we know we can neglect that as well. So once again, I'm only looking at the principal reaction. So typically, if I was given carbonic acid directly, then I would worry only about the first K, okay, the first equilibrium. If I was given something like sodium bicarbonate, then I'm going to worry about the second equilibrium. So I'm going to only use the principal one of that species I'm dealing with, okay? So the second one has HCO3 minus involved, so I would worry about that one. Now that's not something we're going to handle in this class. All we're going to worry about is the principal action of that acid, okay? Principal reaction of the acid. We're not going to get into any salts dealing with equilibriums of the polyprotic species. Now, each equilibrium has an associated acid ionization constant, which we'll write the same way we did in the past. Okay, that would be your products over reactants with your water being a liquid to 1. So we would set that up the same way as before. Major difference is, since we have two equilibriums, we're going to have to be able to distinguish between them. So since it's the first equilibrium, we're talking about your first proton, talking about the loss of one proton. Okay, the loss of one proton, we refer to that as a K1. So it'd be hydronium ion concentration times your bicarbonate ion divided by your carbonic acid equal to the value of K, which is Ka1 at 4.3 times 10 to the minus 7th. Now we do things by one proton at a time. So we have our first equilibrium, then we have our second proton that will come off. Okay, so now we're talking about the loss of a second proton. So that equilibrium will be set up as HCO3 minus plus water gives me hydronium ion plus CO3 minus. We'll set that up the same way, products over reactants, water equal to 1. But in this case, since we're talking about the second proton ionization, that second one come up, we're going to call it Ka2. Okay, Ka2. Now notice the size of your K, 10 to the minus 7th versus 10 to the minus 11th on the Ka2. That's going to continue to get smaller as you go from higher Ks because of the fact of the charge. You have that negative charge, so it's going to pull on that proton more, which means it's going to ionize less. And as the higher that charge gets, the less it's going to ionize. So typically your Ka1 is larger than Ka2, which is larger than Ka3, etc. So in general, the second ionization constant Ka2 for a polyprotic acid is smaller than that of the first ionization constant Ka1. It's harder to pull off that proton because of the charged species. Your total hydronium ion is the sum of all equilibrium, but typically what we do is neglect all but the principal one, only that one in which the species is part of. In the case of a triprotic, the same thing. Let's look like that's for phosphoric acid. You have H3PO4, H2PO4 minus would be the second equilibrium, and HPO4 2 minus would be the third equilibrium. Since H3PO4 is neutral, there is no charges on it, it's going to ionize more than that one with the negative charge. And the one with the negative charge is going to ionize more than the 2 minus. So if you're talking about Ka's values, we know that Ka1 will be much larger than Ka2, and Ka2 will be much larger than Ka3. If we were doing some problem and I was dealing with some species H3PO4, phosphoric acid, then I'll be using the Ka1 expression. If I was doing some sodium H2PO4 compound, then I'll be dealing with the second ionization. If I was dealing with sodium biphosphate be dealing with the third equilibrium. So the species I'm dealing with is the one that I'm going to use the equilibrium as my principal one. As I said, won't be a problem in this class. We're mostly going to have that pure acid or trying to calculate the conjugate base at the end. We're not going to deal with polyprotic salts in this class. Now, when several equilibrium occur at once, it might appear complicated. As we said, we tend to do some reasonable assumptions to simplify things. Let's look at the next example. Okay, I'm starting with ascorbic acid. That's vitamin C. It is diprotic acid. That's why you get just two protons in the front. Okay, so it's going to ionize twice. So first equilibrium, you have your acid, your ascorbic acid forming hydronium ion and your biadsorbate ion. Then that will go on and ionize to form hydronium and your adsorbate ion. So there's two equilibrium. Since we're dealing with the pure acid, then we're going to have to deal with the pure acid equilibrium. So we'll be dealing with the first equilibrium. Okay, notice that both Kas were given to you. You have to pick the right Ka when you're doing the problem. Well, since I got the acid, I will be using strictly that first ionization. We're going to go ahead and neglect the water contribution, as well as we're going to neglect that contribution coming from that second equilibrium, since we have the pure acid. So we set this up the same way we did with the other ionizations. You write your equilibrium, you have your acid, water's your base, so it's going to donate one proton. Okay, one proton at a time we donate, which forms hydronium ions and our conjugate base. Hydrogen adsorbate ion. Plug in our initial values, set up our ice table. We've got 0.1, approximately 0. Once again, when we're neglecting that water contribution as well as that contribution from the second equilibrium, and 0 for our conjugate base. Since I have a zeros on the product side, we know that it has to go to the right. That means I have minuses on my reactant side and pluses on my product side. I need some relationship of change, so we're going to call everything X. So I'm going to consume X amount of my reactants and produce X amount of my products. Notice in all this acid-base stuff that it's typically going to go to the right, and we're always going to be 1-to-1 mole ratio. We do everything on a one proton basis. Do my calculation, I get 0.1 minus X, X, and X. An important question now, which becomes more important now than it did before, is how are these three values related? How is 0.1 minus X, X, and X related? Now you have two choices, Ka1 and Ka2. Okay? So since this is the first equilibrium of ionization, then these are all related through what? Ka1. Okay? If I was dealing with the second equilibrium, it'd be Ka2. So now I'll set that up. Hydronium ion concentration times my hydrogen adsorbate ion divided by my ascorbic acid. Plug in my values. X for hydronium, X, 0.1 minus X. I get X squared over 0.1 minus X is equal to 7.9 times 10 to the negative fifth. Now I want to see if I can eliminate that X, so I can compare my concentration of my acid to the Ka. If I do that, I get a number of 1265, which is way larger than 100, which means yes, I can neglect the X. We also could look at the concentration, which is 1 times 10 to the negative 1. So I'm looking at 10 to the minus 1, compare that to 10 to the minus fifth. And I see a factor of 410 differences, which means by our rules 3 or more that we can neglect it. So once again, we can neglect X. Okay, either way is fine of making the decision. Which gets us X squared over 0.1 is equal to 7.9 times 10 to the negative fifth. Mathematically multiply it through by my 0.1, which gives me 7.9 times 10 to the negative 6. Which now I got to take the square root of both sides. Which gets me X is equal to 2.8 times 10 to the negative third molarity, or another way of putting it, 0.0028 molarity. Now once again, this is an important question. What does X represent in this problem? And this problem X would represent the hydronium ion concentration as well as that conjugate base. That's important because eventually X will maybe equal to hydroxide if we're talking about bases and where errors happen. Now that I have the hydronium ion concentration, I want pH. That's simply the negative log of my hydronium ion concentration, which is 2.55. The last question I want you to ask yourself is, does the answer make sense? Well, this is an acid. Is that an acid pH? Yes, so therefore we have a chance of being correct. Now, we basically neglected the second equilibrium because we wanted the pH of that solution, of that pure acid. Now I want to take the same question and go one step further. Okay, and I want to know, what about the concentration of the conjugate base in that second equilibrium? So we'll take this same question, okay, that initial question, and now we want to know, what is the concentration of the absorbate ion in the previous example? Okay, so where's the absorbate ion coming from? Well, it wasn't part of the first equilibrium. It's only part of the second equilibrium. Okay, so we need to find it, which is basically in that second equilibrium. So we need to go through the first one and then do the second one. We already did the first one, and from the first one we know some information. We know from the first one the concentration of our hydrogen absorbate ion, and we also know the hydronium ion concentration coming from that first equilibrium, and we know we have none of that absorbate ion to start with, which is what we're looking for. So we do the same calculation with the second equilibrium. So if you go back to our first equilibrium, okay, we already worked this problem, and we know that we got 0.0028 molarity of hydronium coming from that, and we have 0.0028 molarity of the hydrogen absorbate ion coming from that first equilibrium. We need to take these values now and then do that second equilibrium. Okay, we need to do the second equilibrium now. Okay, so you write your reaction. So you have your hydrogen absorbate ion plus water. We know by acid base that this is going to donate the proton, which gives me hydronium ion in the absorbate ion, which is what we're looking for. Okay, that's what we're trying to find. Even though I have 0.0028 concentration of hydronium on the product side, I still have 0 of the absorbate ion. Therefore, this reaction still has to go to the right. So I have my minus chains on my reactant side and my pluses on my product side. I need some change. Instead of using X, I'm going to use Y. So I'll make it Y, Y, and Y. Combined in that equilibrium, I get 0.0028 minus Y, 0.0028 plus Y, and Y for the concentration of the absorbate ion. Now, it's important that when you do these problems that you write the reaction and write the ice table. You don't want to just write numbers and multiply and get answers. You want to make sure you're writing everything out. That way you keep track of what's going on and be able to know what Y equals or X equals, whatever the case may be, and do your calculation. You don't want careless mistakes to make problems for you. For example, right here, you need to ask yourself a question. How are 0.0028 minus Y, 0.0028 plus Y, and Y related? They are all related through the reaction we wrote just now, which is what? Ka2. Okay? If you just multiply numbers and not paying attention, you may choose the wrong K. So it's best to take your time and write out everything. So we write our equation, we write our table, ask ourselves the question, what is that related through from this equation, which in this case is Ka2. Write out my Ka2, which is the concentration of my hydronium times my absorbate ion divided by my hydrogen absorbate ion. Plug in my values. 0.0028 plus Y for hydronium, Y for my absorbate ion, and 0.0028 minus Y for my hydrogen absorbate ion, which gets me 0.0028 plus Y times Y divided by 0.0028 minus Y equal to 1.6 times 10 to the negative 12. I want to get rid of the Y's if I can. So I'll compare my concentration of my species to my Ka. Mathematically, if I do that, I get a 1.75 times 10 to the ninth, which is way larger than 100, which means that I can eliminate my y. And that happens in both cases, the plus y and minus y, because I'm comparing the same number, 0.0028, to that 1.6 times 10 to the negative 12. Or I could look at powers of 10. 2.8 times 10 to the negative third is what 0.0028 is. Compare 10 to the negative third to 10 to the negative 12. That's way larger than 3 powers of 10 difference. Therefore, I can neglect my y. Which gets me 0.0028 times y divided by 0.0028. Which gives me 1.6 times 10 to the negative 12. Well, mathematically, what do you think is going to happen to the 0.0028? They cancel. Which leaves me y is equal to 1.6 times 10 to the negative 12 molarity, which gives me my concentration of my adsorbate ion, which is what we're looking for. It also tells me the concentration of my hydronium ion coming from that Ka2. Okay, it's telling me my amount of hydronium ions coming from that Ka2 equation. Now you might notice something, that Y basically is the same thing as Ka2. Typically, the concentration of the anion ion equals the Ka2 of starting with the reactants of the first equilibrium. So for our purposes of diproducts, you're going to have a pure acid, or I want to calculate the conjugate base of that second equilibrium. Very straightforward calculations. It gets more complex than that when we start dealing with other calculations, but I'll leave that to quantitative analysis and not here. I prefer to concentrate on the monoproduct stuff to make sure we get that straight. But I will introduce you these concepts and in the homework, the things in the homework are what you're responsible for. Another reason I like to do this problem is for you to see how the concentrations of those other equilibriums do not affect the total concentration. So let's look at those values. The total hydronium ion concentration will be 0.0028 coming from that Ka1. We got 1.6 times 10 to the negative 12 coming from that Ka2. And we got less than 1 times 10 to the minus 7 coming from water. Remember that equilibrium is going to shift it, so it's going to be less than that, but I didn't bother to calculate it. Let's compare the numbers. How much effect would 1.6 times 10 to the negative 12 have on 0.0028 if I add them up? None. I mean, that's several powers of 10 difference. So it's not affecting it. What about 10 to the minus 7th? And remember, it's smaller than that because we're going to do some shifting by adding other concentrations of hydronium. How much would that affect 0.0028? None again. Okay, so in essence, what I'm showing you is that those last two can be neglected, and that's why we can just say concentration of that first equilibrium is the concentration of our final answer. As I said, homework number 30 is going to deal with polyprotic species, but the homework questions are what you need to be responsible for. We're not going to go into salts of our diprotic species, etc. We handle that later on in chemistry.